So, then another problem that I want to describe in this lecture is the problem of geodesics. Okay. So, this is a problem which is widespread in the area of differential geometry. Right. So, the problem is as follows. Let us assume that sigma is some surface. It could be a surface of a sphere, it could be a surface, any particular surface, and let us say that P0 and P1. Now, for easier reference, let us say this is my surface denoted by sigma, and let P0 and P1 be 2 points on this surface. Okay, be 2 points on this surface sigma. The geodesic problem says we need to figure out the optimal curve. We need to figure out the optimal curve sigma with minimum arc length. Okay. So, we have to figure out the curve passing between the 2 points P0 and P1, so that the total length of the curve is minimum. Now, intuitively we can see that the length will be minimum when this curve, let us say on a 2 dimensional surface, this curve is a straight line, right. But we will show using calculus of variations that indeed that the extremal solution that we get from the geodesic problem is indeed a straight line. Okay. So, a bit more in depth detail of this problem. Let us say we denote sigma by the position vector r from small sigma to r cube, where in terms of notation my small sigma is a non-empty connected open set, non-empty connected open set. Okay. Set or I would say a subset of R2. So, sigma is a subset over the class of all these surfaces, which is the subset of R2. Okay. And then, so I describe any of my surface by a 2 parameter family, let us say u and v. So, let us say u and v belongs to sigma, which is the class of this surface, and in that case my family of curves on this surfaces is described by r, which will be a function of u comma v, which is going to be in terms of its position vectors x of u comma v, y of u comma v, z of u comma v. Okay. So, it turns out that the set of, I can further simplify this description of these optimal curve using a single parameter, let us say t. So, let us say the set of all smooth curves. When I say smooth, I denote continuous / piecewise differentiable curves. So, set of smooth curves on sigma, we denote it using the parameter t, such that t is taken from some interval along the real axis t0 to t1. So, in that case the set of all smooth curves which is going to lie on this surface, we denote it by capital R of t, which is eventually going to be r of u of t comma v of t, right. So, we see that the curves will be found by substituting particular values of u and v in this position vector, and as we move along these curves, the value of this parameter t, it changes, okay, from t0 to t1. Okay. So, in this case my arc length, let us say arc length element ds square is going to be, by chain rule it is going to be r prime t, let us say the absolute value, because this is the length. So, length can never be negative. So, arc length square is absolute value square, absolute value square times dt square. Okay. So, then when we open up this absolute value, that is, this is r prime t dot with r prime t dt square, we can rewrite this arc length element as follows, that this is also equal to r of u times u prime plus r u dot r v times u prime v prime, and that is twice plus r v times v prime square, okay, times there is no square involved here, times dt square, where my r u is del r, partial derivatives of r with respect to u, and my r v is partial derivative of r with respect to v. So, further I denote my r u or absolute value of, so r u, it turns out to be r u square, r u r v times and then r v square. So, that is the correct expression in this case. So, it turned out, let us for simplicity denote E to be the absolute value of r u square and f to be r u dot product with r v, and my expression r v mod r v square to be g. So, the geodesic problem says that the geodesic problem says that we want to minimize L, which is the integral of the square root of the arc length. Okay. So, the integral of the square root of the arc length square, which we substitute from this following expression above, which is also equal to integral from t0 to t1 times square root of E times u prime square plus 2 f times u prime dot with v prime plus g times v prime square dt. Okay. Subject to u of t0 is u0, u of t1 is u1, and v of t0 is v0 and v of t1 is v1. Okay. So, these are my boundary conditions in terms of the parameters of the system. So, just to give a brief overview, let us say we are considering the surface as the sphere. So, on a sphere I can denote my surface r of u comma v by the following set of functions. My coordinates are sin u cos v comma, that is my x coordinate, times sin u times sin v, and finally the z coordinate is cos u. Okay. And then if we are to use this formula above, we see that my arc length L turns out to be, by substituting all these values for this x, y and z, my arc length functional comes out to be u prime square plus v prime square sine of sine square u dt, where my primes denote the derivatives of these parameters u and v with respect to the parameter t. Okay, and so that is a particular case. Moving on, let us look at a related problem. Let us look at a related problem, that is to find the minimal surface. The minimal surface similar to the catenoid problem. I can refer this problem as the generalized catenoid problem that I showed earlier. Okay. So, in this case the problem says we have to find, again this is the geodesic problem, but in two independent variables. The problem says we have to find the surface, having minimal area among all smooth simply connected surface with a given boundary gamma, such that my area element in this case is going to be similar to the arc length construction. My area element construction will be square root of 1 plus zx, where this is the derivative of z with respect to x, plus zy square dx dy, right, where my z is the height of the surface and x and y are my independent variables. Okay. So, in this case my area functional A of z turns out to be a double integral over the surface. So, double integral of this area element 1 plus zx square plus zy square dx dy. So, we see that in this case the optimization involves a functional of two independent variables x and y, and we will deal with similar class of problems later on. Okay. So, then let us now move on to another problem in economics. Okay. So, this fifth one, or the last problem of this lecture series, is the problem of finding the optimal harvesting strategy. So, the problem is, well, this could be modified into a problem in several areas, but the classical problem arises in economics. So, the problem is to find a harvesting strategy, let us say of fishes in a pond. So, we have to find the harvesting strategy that maximizes profit. So, the fisherman has to harvest so much quantity of fish, so that he or she can get the maximum profit out of it. So, let us say that the growth of the fish population, follows an ODE of the form y prime t, which is equal to f of t comma y, where where I denote my y to be, so y to be my fish population at any given time at any given time point t. Okay. So, then let us further assume that the fish cannot grow indefinitely, which means that there is a carrying capacity of the fish, let us denote the carrying capacity by yc, right. So, yc is the carrying capacity of the fish, which means that I am going to model the growth of the fish, which is I am going to denote this left hand side, sorry, the right hand side of this ODE given here by the logistic curve. So, the growth could be modeled using the logistic curve. Okay. So, which means that my right hand side of my ODE will be of the following form. It is k, where k is a constant. So, this is a constant times y of t times 1 minus y of t divided by y of c. We see that when the population exceeds the carrying capacity y c, the right hand side of this ODE becomes negative, right. Well, we assume that the constant k is positive. So, which means that after y c the fish population is going to start to fall. Okay. Further, we assume that there is an initial condition, that is the initial population of the fish at t equal to 0 is y 0, and let us further assume that the harvesting rate, the rate at which the fish population is taken out of the pond is denoted by this function w of t, right. So, which means that this particular ODE can now be remodeled as follows. We are going to remodel the growth of the fish population by this modified growth equation f of t comma y minus w of t, which is the quantity per unit time of the fish which is taken out of the system. Okay. So, then the problem is as follows. The problem is we need to determine the harvesting rate, we need to determine w of t, so that the profit is maximum. The profit in a given period is maximum. So, typically the fishermen, they want to take out fish in a particular season of the year. So, let us say this period is a particular season of the year where the fisherman wants to maximize the profit. Okay. Let us denote this period by t. So, then let us now quantify this problem. Let us say that C be the cost of harvesting. So, C is the cost to harvest per unit biomass or biomass of the fish, right. So, of course, the cost will depend on the particular season, it will depend on the fish population in the pond as well as the harvesting rate. And then let us say that P of t is the price of the fish that is sold on in the market, the price per unit mass of the fish which is sold in the market. Okay. So, which means that my profit functional P of y comma w is the following functional integral from 0 to t, the total price of the fish minus the cost to harvest that quantity of fish times the harvesting rate of the fish dt, right. So, let me denote this by 5. So, we need to find the goal of this problem is we need to find W of t such that 5 is maximum, and subject to the constraint y prime is equal to f of t comma y minus W of t. So, we have that the fish population must satisfy this ODE constraint. We see that this particular constraint now is not an integral constraint, it is a differential constraint, and hence the so called holonomic constraint. Okay. So, we are going to deal with the class of problems of extremizing functionals with holonomic constraints later on. And of course, we have boundary conditions, or I would say initial conditions in this case, which is given by the fact that y at t equal to 0 is y 0, right. Now, one can always say that an intuition tells us that perhaps the profit of this functional 5 can be maximized when all the fish is taken out of the pond, right. So, one intuition tells us that the boundary condition when over the entire length of the catching season the total fish is taken out of the pond, or y at t equal to 0 is perhaps the optimal solution. It turns out that this is not the case, this is not. So, the boundary conditions, this is not the optimal case, because it turns out that as we harvest more and more fish from the pond, it becomes more and more expensive to harvest the fish, right. So, because harvesting is more costly, with fewer fish in the pond, Okay. So, let me wrap up this lecture session by giving you some more problems that we are going to disclose and talk about in more depth. So, the problems that we are going to talk about over the later lectures are the problems of reduction of vehicle drag, also known as the class of problems related to the Newton's aerodynamic problem. So, the vehicle design with minimum drag. The class of this problem belongs to the Newton's aerodynamic problem. We will go through this in detail over another lecture. Another problem that I am interested to go in depth is to find the optimal shape of a soap bubble, with such that the curvature is minimum, right. It turns out that the lower the curvature of the soap bubble, the lower is the total energy or the surface energy of the soap bubble. So, nature provides the shape of the soap bubble such that the total energy of this system is minimum, right. Then another problem that we are going to talk in detail is finding the shape of cantilevers or bending beam problems, cantilevers or buckling beams, buckling beams in atomic force, let us say atomic force microscopy, right. Well, the class of this is just one case, microscope. So, this is just one case of the class of problems that we are going to describe, and this class of problems belong to the class known as elastica, which we will also talk in more depth. So, thank you very much. So, that is the end of this session. Thank you for listening.